Today we're going to be talking about motors and how their direction is determined. Um, how come when we start a motor, it doesn't just turn in a random direction when we start it up, but it's deterministic which direction the motor is going to spin when we run it. And also there's some distinctions, some pretty good distinctions about how that's accomplished in a three-phase motor versus a single-phase motor. A three-phase motor, which would be receiving power from our uh, utility distribution system. And if we have three-phase coming in, we can provide that three-phase directly to a motor, and it just works. Whereas with single-phase motors, it's a little bit more complicated. So today, what we're going to be going over, just to do a quick overview, is going to be reviewing changing magnitude of electromagnetic fields. We sort of discussed this a few weeks back when we talked about transformers. We talked about electromagnetic fields, that when current flows through a conductor, an electromagnetic field is created, which increases or decreases in magnitude depending on how much current flow. And of course, current flow being directly proportional to voltage. As voltage increases, current increases, and also then your electromagnetic field will become larger. So we're going to review that. We're going to come to an understanding of how three-phase motor rotation is determined. We're going to come to an understanding of how capacitors will create a phase shift. And we're going to come to an understanding of how single-phase motor rotation is then determined. Has anybody here had any previous education about capacitors, inductors, and how leading voltage leading current versus voltage lagging current, and how that might create a phase shift? That's okay. So this is going to be some material that's going to be pretty new to everybody, or most folks here. So just try to really focus on what we're discussing. Try your best to grasp the concepts. I'm going to try to explain some of them in a few different ways to help visualize and understand what it is we're chatting about here. So we're changing electromagnetic fields. So if we were talking about direct current, we would have a consistent voltage being used in our circuit. And 24 volt DC is always 24 volts. It's static at 24 volts, right? It doesn't increase, it doesn't decrease. It's just unless it's a battery, and so maybe you'll have some lowering of your voltage as your battery drains, something to that effect. But if we have a consistent voltage input into our DC system, we're going to get a consistent DC voltage output. It's not going to change. Whereas with alternating current, voltage is not a static value, right? When you put your meter across line 1 to neutral, line 1 to L2, or what have you, what you're reading is actually what they call RMS voltage, or root mean square voltage. You're not exactly reading peak voltage, but you're reading what they call a root mean square voltage. So like your actual peak voltage when you read 120 volts is higher a bit to under 20 volts, but you're actually reading the voltage somewhere where it clips the peak in either direction. But in reality, 60 times a second, that voltage is changing from 0 volts. So we have a 0 reference line in this on this sine wave graph, this measurement of magnitude. We'll start with 0 voltage, and then our voltage will actually be all voltages between 0 and whatever it is we're reading. And then that will increase and decrease 60 times a second. And so knowing that, then when our voltage is at 0, our current is at 0, and also the magnitude of our electromagnetic field is 0. And then all three of those increase proportionally as voltage rises and falls. All right, so they are going to be strongest at their peaks. All right, so this is the peak in the positive direction, and this is a peak in the negative direction. Now, when we're talking about three-phase systems, we have three different phases. We have three conductors, right? We have when we're wiring our buildings, a three-phase system is going to have A phase, B phase, C phase, and then neutral, which is going to be our reference line, 0, right? And so if we were to measure our voltage of A phase, B phase, and C phase, shown as phase 1, 2, and 3 here, if we were to hook up an oscilloscope to our system and read those voltage, we would notice that each of the phases peaks at a different time. We call this a phase shift. These are 120 degrees out of phase with each other. And what that just essentially means is that at a different moment in time, each of these is going to be at peak voltage. So we can see phase one's at peak voltage at this moment in time, but phase two is not at peak voltage. And it's in the opposite direction, right? If we just look across, we can see that these aren't peaking at the same time. Now, phase one, as it decreases, we can see now phase two is at peak, and phase one is where phase two was. And then so on and so forth. Phase three does the same thing, and then that pattern just repeats and repeats 60 times a second. So the direction, when we're talking about hooking up motors, the direction of the motor is determined by the sequence in which those phases reach their peaks as to how we have wired that motor. So if we were to wire that motor, if that motor leads, we'll call them T1, T2, and T3. If we wire T1 to line 1, T2 to line 2, and T3 to line 3, what we should expect to see is what we call a clockwise rotation. And then if we reverse that, we should expect a counterclockwise rotation. We're going to actually get into that a little bit more on a future slide. Who here has actually needed to reverse a three-phase motor? You ever, wire up an AC unit, an air handler unit, rooftop unit, what have you? You kick it on, and all the compressors just sound bad. Instead of our return air is acting as supply air and all that. Has anybody experienced that?
Yes. Oh yeah.
Yep, that's something that we experience rather frequently, and it's something that whenever we are hooking up equipment, three-phase equipment, we should be checking the rotation. Sometimes you can't actually start the equipment, and I didn't really develop this into this presentation, but if you have a phase rotation meter, you can at least check that your rotation at your terminals is correct if you're unable to actually start the equipment. That may be something that I go over in a future presentation, because that is kind of a neat thing to do, and most of us have probably never even touched a phase rotation meter, but it's actually really easy to do. So good. So we've had some experience with that. So if you have a three-phase motor that is running in the wrong direction, if we swapped any two phases, actually this graphic is, there shouldn't be a neutral connected to our center point on a motor. That's not correct. So ignore that on this if you would. But if we reverse any two leads, L1, L2, just swap them, L2, L3, it doesn't matter. We just swap any two leads on this, the motor will then turn in the opposite direction. One quick aside on that, if you have a system that has VFDs, variable frequency drives, and you have a rotation issue, you have to reverse the leads on the load side of the VFD, because if you reverse it on the line side, the VFD is going to determine the direction it wants the motor to spin, and it does some kind of torque calculation, and it knows when it starts what direction it's spinning, and they'll often make a correction inside the VFD. So if you have a VFD, it's operating in the opposite of what it's programmed to do. You programmed it to run in a clockwise rotation, yet the motor is spinning clockwise or counterclockwise, then you have to reverse those leads on the load side of the VFD. Okay, so this is a little bit more on that same topic. Is by changing the leads, what we're effectively doing is we're changing the direction of the electromotive force that we are presenting to that motor, that we are inducing in that motor, right? And so in this graphic here, on the top graphic, we can see we've drawn a circle with arrows indicating the direction of rotation. And if we follow A, B, C, we can see we go from A, B, C, and we're rotating clockwise. If we swapped B and C here, so now we can see, if we look between the two slides, C and B have changed position. And then we look from A, B, C, we can go A, B, C. We can see how our rotation will spin in the opposite direction. The reason this works this way is because what we previously said is that the direction of our rotation is determined by which phase peaks first, right? So A phase will peak first. It sort of depends on where you measure it, but it's a pattern, right? And the pattern's not going to change. So if we go from A, B, C, A is going to peak first, B will peak second, C will peak third. Okay, so that's one way to think about, okay, which direction is this motor going to turn? Well, it's going to start turning in the direction of A. It's going to continue turning in the direction of B, and then proceed and just continue to turn in the direction of C, and start over and over and over again. Yeah, so we're changing the order in which that motor is wired and receiving the magnitude of the electromagnetic field. But the other thing we're doing, and this is a little hard to visualize, But the other thing we're doing is we're actually reversing the direction of the rotating magnetic field in that induced coil by swapping those leads. That's how that works. The theory is kind of neat, but if you're in the field and you just want to reverse a motor, you don't need to know the theory. Just know, okay, in order to reverse this motor, I need to swap any two leads. And if I have a VFD, I have to do it on the load side of the VFD. If you take nothing away from this, if you know that much, then you'll be able to get that equipment running the way it needs to. Now, what happens if we only had two phases supplying power to a three-phase motor? Well, and I'm going to sort of jank up this explanation a little bit. But effectively, what that third leg does is it provides enough torque to overcome the inertia. So if we only had two phases connected, maybe A phase and B phase, this motor, like if you looked at the shaft of the motor and you only had 2 out of 3 phases connected, you might see it like move just slightly. It's not going to move much because there's actually, this represents a pretty broad, gap in this pinwheel graphic. Actually, the in the stator, the phases change a lot closer to each other, so you're not going to get that much movement. It's going to pretty much just move and stop, more or less in between these two phases, because it's going to sort of find that equilibrium between the magnitude of the two phases and then just pretty much stop. It's not going to keep moving. So that third phase, what that third phase does is it allows this motor to overcome the inertia enough to keep moving. And as it does, it's going to build up speed. And once it builds up enough speed, it's going to just keep rotating in the direction that electromagnetic field is rising and lowering. Because like A phase is going to peak first, so we can sort of picture that rotor start to spin in the direction of A phase. But A phase is going to lower as B phase rises, right? And so B phase is rising, but then if there's no C phase, it's like, okay, what do? Well, I guess I go back towards A phase because it's rising. Okay, and now I'm going to go back towards B phase, and it's just going to be like it's not going to know which way to go. You're actually going to hear that, sort of noise. There's some humming happening there. It just doesn't know what to do. But if you just introduce that third phase, now it's like, okay, I'm going to keep going. And so you'll have A phase peaking, B phase, and then A phase will start to dip, B phase will start to rise, and then B phase will start to dip while C phase rises, and then A phase is going to rise. And so it's always moving in the direction of the strongest magnetic field, and they're all rising and lowering in order with each other. So hopefully that's enough of an explanation to sort of like understand how that all is going to work. Now, with a three-phase motor, even a single phase, with single phase or three-phase, if they both actually require 3 phases, and we're going to get into that. If it's a delta wound motor and it's already running, I believe it'll actually continue to run. It'll run less efficiently, and it might only run until the winding that is picking up the slack fails or the thermal overloads fail. It's called single phasing. I've never really seen it in my career because we don't really do a lot with motors, but we can see that in a delta configuration that we actually still have current on all 3 of our coils. But if you only had 2 legs, like I said, it either won't start, but if it's already running, it could continue to run just much less efficiently and until either it fails or the thermal overloads open. Okay. So effectively what I'm saying is that by introducing a third leg, we're providing efficient starting torque for the motor to begin to spin in a deterministic direction, always in the direction of the strongest magnetic field. So it's just going to follow that magnetic field, as it strengthens. Cool. So we know how 3-phase motors turn. We have 3 legs. The third leg provides that additional torque to keep that motor spinning in the same direction and build up enough momentum. Great. So it's pretty straightforward for 3-phase motors, but then how do single-phase motors spin? Right. We don't have the third phase to establish torque. The way the motor itself is wound, this is sort of similar to how when we talked about single-phase transformers, how you get a split phase out of a single-phase transformer is by winding. You have an incoming voltage and you just wind that iron core, but you do it in one direction and then you wind it in an opposite direction. And by doing that, your current is flowing in 2 different directions on that core. So you effectively split a phase, right? And so you can get the two poles that you need out of the three with single phase when you wire that, when it connects to that motor. But how are we getting that third phase? Well, we do that with capacitors. Now, a capacitor is a device. I'm sure we all like know what capacitors are, and it's like the first thing you think about when your AC unit goes out. Like most of us, we should think, oh, my AC unit's not running. What's the first thing you're going to check? Probably is the capacitor. It's the part that fails the most frequently. It's also the cheapest component in the system to try if you're just part swapping. What I would imagine, I don't know if our AC guys do this, but I would imagine if we're going to do a service to an AC system, I don't know, maybe we just change the capacitor. I don't know, maybe there's a regular maintenance there. But basically what a capacitor is a device that builds a charge on conductive plates that are separated by a dielectric material. So we have a charge that's going to build on a dielectric plate that's going to be positively charged, and as that charge is building, you have positive charges on one plate that are pushing away a negative charge on the negative plate. And so as it charges, there's current flow happening. But our charge, our voltage, our potential is not at full potential. That takes time to build. In terms of electrical time, it's like an instant, but it's still relative to electrical time. There's still time passing, and it takes longer for voltage to build than current to build. But we know what capacitors are. Like, it's a device that builds a charge and then releases a charge. So an important concept to understand why we're even talking about capacitors. If we want to understand why we're talking about capacitors and how a single phase motor spins, if we want to understand it, we need to remember Eli the Iceman. I suppose you don't have to remember Eli the Iceman, but I've always remembered it since high school. Eli the Iceman. So I'll tell you what what this stands for. So Eli, the ELI and ICE, these are all your characters that represent a value, right? So E being voltage, L stands for induction, C stands for capacitance, and I stands for current. So if we're talking about an inductive circuit, so a motor is an inductive circuit, a transformer is an inductive circuit, or a load, I should say load. These are inductive loads. In an inductive load, voltage is going to lead current, so E being in front, right? And so in a capacitive circuit, current is going to lead voltage. So what that means basically is that in a capacitive circuit, you already have voltage potential at full potential before your current is at the full equal value to that potential. I know this is going to be a bit confusing if you haven't heard these things before, but that's okay. Whereas in a capacitive sense, your current is at full current before your voltage is at full voltage. Right? So we're leading or lagging. We call that leading or lagging. So with inductive leads, the current with inductive loads, current leads. With capacitive loads, currents lag. Okay, so there's an opposite there. I wanted to explain this in a few different ways. And I'll tell you honestly, when I was studying this last night, this was about 3 hours of study for me to sort of like, what the heck is this? Like, how do I understand this? So it's fine if you're having any difficulty with this, because I certainly did, and to an extent still do. But all of us humans are capacitors. We build a capacitance. We've probably all experienced walking across a room, especially in the winter. In Florida, a lot of humidity, so maybe you don't experience that much. In Massachusetts, where I'm from, from where I came from, we have a pretty long dry season. So during the dry season, you're not, the environment, if it's humid, you're able to stay at an equal potential to your environment. But I'm kind of getting off track here. You are a capacitor. You can build a charge. You've all experienced building a static charge, touching a doorknob or what have you, and feeling that little shock, right? So like a capacitor, you can gradually build up a charge as you move across something like a polymer rug or something like that. So think of your movement, you moving across the room, think of that as current. Those are your electrons, and it's happening, right? But your potential is not building up immediately. The longer you walk across the room, the longer it takes before you touch something conductive, the higher your charge is going to become. So your voltage, your potential, is sort of lagging your movement. I don't know if that helps, but I was trying to think of a way to visualize how the charge in a capacitor will allow some current to flow through it. It doesn't actually flow through it, but as a charge builds on one plate, it repulses the opposite charge on the other plate. But the actual potential of that capacitor sort of lags. Cool. So how is this useful in single phase motors? In a single phase motor, we introduce a capacitor into the circuit, whereas with a three-phase motor, you're just providing the utility power directly to the motor. With a single phase motor, we introduce a capacitor into one of the windings on that motor. And by doing that, we talked earlier that with our single phase, if it's 120 volts, then we're doing split phase, right? So the windings we would just wind the motor from that one leg coming in. We would wind that motor in two different directions in order to create a split phase. So that's giving us two legs in opposite with electromagnetic potential fields in opposite directions. By creating that phase shift with the capacitor, now we can wire a third leg that is that has a phase shift relative to those other two legs. If none of this makes sense, if my explanation was garbage with all this, which it may have been, just remember, why is this capacitor in the circuit? It is to create a phase shift with that third leg. That's all you really need to remember. The capacitor produces a phase shift in the third leg. It's not there to give a high charge, a high release of electrons so that the motor like gets a jolt in the right direction. It's not what it's doing. It's just creating that phase shift so that motor doesn't just get stuck between two poles that are just changing position. It has that third pole to like start movement and then keep moving in the direction of that third leg. So here's a diagram of a single phase motor with a run winding and a start winding. This is a pretty generic photo. But what the motor will have is a run winding. So the running winding are the windings in the motor that will stay in the circuit 100% of the time. As for the entire cycle that motor is spinning, that winding stays in the circuit 100% of the time. Typically, these windings, the wire is a little bit larger in comparison to the start winding, and that's mostly done for cost savings, and especially as it relates to this particular photo, because there are some that actually will have two capacitors, a start and a run capacitor. The capacitor in the video I might explain that a little bit. But this is just a very simple representation. So we have your line coming in, feeds our run winding, and then we also have off of that same line coming in, we have a wire that comes up, hits our capacitor. On the opposite side of the capacitor, we attach to our start winding. And then from the opposite side of our line circuit, we're hitting what's called a centrifugal switch, which in this illustration, this is actually shown in a running position, because if this were at rest, this centrifugal switch should be closed, and then it attaches to the other side of the start winding. So, and then after the motor starts, let me back up. So having this circuit set up this way, we have an additional winding that's going to represent our third phase, our third leg here. Now, after the motor gets up to speed, the centrifugal switch will open and it will take the start winding out of the circuit, which might seem a little counterintuitive, because we said, well, how does the motor keep its rotation then? Because we need all three phases, right? The video I'm going to show in a moment is actually going to explain that pretty well. So if you have that thought, just hold on to it. Now, if we want to change the direction of this motor spins, then just like with a three-phase motor, we would swap two leads. But the leads we would swap would be the leads that go through your start winding. You wouldn't swap the entirety of the leads. You wouldn't swap all of them. You only swap the two that go through this start winding. And then that will change the direction of current flow through your start winding, which means that voltage is now going to peak in a different order relative to your run winding, just like it does in a three-phase motor, and you will effectively change the direction of the motor. All 120 volt motors are reversible this way, except for the fact that manufacturers don't make all motors in a way where it exposes the start winding to the installer to be able to switch. So if you are doing an installation where you need to reverse a 120 volt motor, make sure what you're purchasing is one that is designed to be reversed. And it really just boils down to whether or not the manufacturer has exposed these leads to be reversed. And if you watch this entire video that I'm about to show, that goes into greater detail about it. It's a really good video and explains a lot of this this stuff in another way that helps drive the points home.
For three-phase motors, the sense of rotation is inherent in the three phases coming into the motor, but for a single-phase motor, like this split-phase induction motor, a sense of rotation has to be created with a bit of trickery using a capacitor. This is the schematic for the induction motor, where we have two windings that are at a right angle, and one of these windings is connected directly to AC, whereas the other one is in series with a capacitor. On this induction motor, one of the windings is these two coils and the other winding is these two coils. So this winding goes this way for magnetic field, the other one this way. And the interaction of the inductance of the coils here and the capacitor causes one of the windings to be shifted 90 degrees. So as this one goes up and down and this one goes side to side, they're out of phase 90 degrees, so we get a sense of rotation. Reversing this type of motor is trivially easy. All I have to do is move the AC from directly to this coil to directly to this coil, and then through the capacitor the other winding is delayed. So essentially all I have to do is move the power connection from here to here. So here's the capacitor, and all I have to do is move this clip to the other side of the capacitor to reverse it. And this becomes much easier to see if I slow down the motor a lot by reducing the voltage. So you can see now it goes counterclockwise, and now I move this clip and now it's clockwise. Now if we look inside this 3/4 horsepower motor, you can see the windings are not as easy to discern. Essentially the winding is split over many slots in the stator here, and that makes the transition from pole to pole a lot smoother, which makes for a quieter, more efficient motor. Looking closely at the windings, you can see there's a winding that goes here, and then there's another one that goes here, and that's made out of thicker wire, and that's the main winding. And then if we have another winding that's kind of to the inside of that, that's made out of thinner wire that goes here and here. So now if I put a compass in here and I put DC through the main winding, you can see we have a horizontal magnetic field, and if I move that clip to activate the starter winding, you can see we have a vertical magnetic field. So those windings are 90 degrees out of phase with each other. One end of the starter winding is connected to this red wire, and that goes to this capacitor, and then the other side of this capacitor goes through this black wire onto here, and that's the starter switch, and that gets disconnected once the motor's up to speed. So the schematic for this motor is very similar to our split phase motor, with one winding directly on the AC and the other one in series with the capacitor on AC, except that this winding is much thinner and we turn off the winding once the motor's up to speed. The starter winding is automatically turned off with a centrifugal switch, and the way that works is these two metal clips get pulled out by centrifugal force once it spins at full speed, and that pulls back this plate here. When the motor is not at full speed, this plate rubs against this plastic tab here, and as long as that plastic tab is pushed, this starter contact is closed, and then once it's up to speed, the plate pulls away and it no longer rubs against here, so we don't get friction and wear. So if the starter winding helps to create a rotating magnetic field to spin up the motor, why disconnect it once the motor is actually up to speed? The whole phase shifting the starter winding with a capacitor is not as elegant as it would sound. The size of the capacitor very much depends on the expected load of the motor, and if we just connect it briefly temporarily at the start, it doesn't matter if it's a little bit inefficient or the wrong size, because we won't leave it engaged. Also, this capacitor is an electrolytic capacitor and is not designed to take a continuous AC load. If it got that kind of load, it would burn out, and to have a condenser for this size motor would be quite expensive. And because we turn off the winding once the motor's up to speed, we can also use a much thinner winding for the starter winding and save a bit of money that way, because copper is expensive. So just to turn off the starter winding makes an awful lot of sense. But once we turn off the starter winding, the magnetic field just goes back and forth, so why does the motor keep on spinning? You can compare that to moving the screwdriver back and forth with this pendulum. Just moving it side to side doesn't get the pendulum rotating, but if I rotate it, now it goes round and round, and now even if I just go side to side, I can keep that thing spinning for as long as I want to.
So to summarize, right, motors are going to require enough starting torque to overcome their inertia, and that's done by introducing that third phase to overcome inertia and to keep it from locking between positions. That's ELI the ICE is are helpful acronyms to remember which what to expect as far as leading or lagging of voltages for either inductive or capacitive circuits. And for single phase circuits, the system starting torque is provided by that capacitor that we introduce in the circuit, and it only stays in that circuit temporarily. in the instance of what we have shown today, it only stays in the circuit temporarily. But there are motors actually that have start and run capacitors. And the difference basically is just that the start capacitor is taken out of the circuit after the system is running. But then there is a run capacitor that is left in the circuit, and they're going to be different designs. In the video we watched, he mentioned how an electrolytic capacitor might be used on a for the start winding, and unfortunately, I'm not educated as to what it's called, but it'd be some different variant of a capacitor than that you would have on that start winding. And then, of course, I think the windings would actually be a heavier gauge so that they can sustain a running current and all that kind of stuff. So we didn't really go over that, but if you're interested, you could look up motors that have start and run windings to get a little bit more, or excuse me, start and run capacitors to get a little more knowledge on that. And then finally, for single phase motors, we can change the direction of that motor by inverting the polarity of the start winding, or effectively just changing which terminals that start winding is terminated across.